Hello everyone, welcome to lecture 10, which is the second lecture of week 5 in linear algebra. So the key concept in this lecture is the concept of a linearly independent set in a vector space. And we'll start out with an example. The relevant section of the lecture notes is section 2.2, which is available on the webpage. So we talked about spanning sets last time. So let's just start with this example in R2, which we regard as the space of all column vectors with 2 entries over the real numbers. So here's a set S of 3 elements in R2, and the assertion is that this is a spanning set for R2. And remember what that means is that every element of R2 can be written as a linear combination of these 3 elements in the set S. So to verify that for ourselves, we can observe that if we have any vector AB in R2, we can write it as a linear combination of the elements of S, and obviously the coefficients that we choose will depend on the values of A and B in this particular vector. But the claim is that, for example, by writing AB in this form, taking the coefficient of 3, 1 to be A plus B, coefficient of 2, 1 to be minus A minus B, and the coefficient of 1 minus 1 to be minus B, then adding up these 3 scalar multiples of those 3 vectors will always give us AB, no matter what A and B are. And we can certainly confirm that looking at the first entry, it's going to be 3A minus 2A, which is A, plus 3B minus 2B minus B, so just A. And looking at the second entry, we're going to get B minus B plus B, so B plus A minus A, so just B in the second position. So for example, if you want to try that out for a particular choice of A and B, for example, if we want to take AB to be the vector 4, 4, for instance, then we should take A plus B, that would be 8 times 3, 1. Plus minus A minus B, that would be minus 8 times 2, 1, plus minus B times 1 minus 1, so minus 4 times 1 minus 1, and we should hopefully be able to verify that that is indeed equal to 4, 4. Okay, so observation here is we've got 3 vectors in the set S here, and we've written down one way of writing any vector in R2 as a linear combination of elements of S. But the assertion for this example is that that's not the only way to do it. For example, we could also write the same vector AB with different coefficients as a linear combination of the 3 elements of S. So again, here's an alternative expression, and we can also verify by just expanding that out that we do get, if we add together the 3 expressions on the right-hand side there. In the first entry, we get 12A minus 10A minus A, so A plus 3B minus 2B minus B, so just A on top. And in the second position, we get B minus B plus B. So B, we get 4A minus 5A plus A. So we just get B in the second position. And so, for instance, if you wanted to use the same vector 4, 4 and write it according to the second kind of framework here as a linear combination of those 3 vectors, A and B are both 4. So 4A plus B would be 16 plus 4. That would be 20. So we get 20 times 3, 1. Minus 5A minus B would be minus 20 minus 4, so minus 24 times 2, 1. And then minus A minus B would be minus 8, so minus 8 times 1 minus 1. And we should be able to confirm by a little bit of addition that these are 2 different expressions for the vector 4, 4 as a linear combination of those 3 elements of S. And indeed, if we believe these 2 equations, then for any vector, we'll have multiple ways of writing it as a linear combination of the 3 elements of S. So indeed, we don't even need all 3 elements of S in order to span R2. We could achieve any vector in R2 as a linear combination of just the first 2 elements of S. And here's a way of doing it. If we have a vector AB in mind, we can take A minus 2B as the coefficient of 3, 1. So if we were to do that with our example here, 4, 4, A minus 2B in that case would be 4 minus 8, so it would be minus 4 times 3, 1. Plus minus A plus 3B, which in this example would be minus 4 plus 12, so it would be plus 8 times 2, 1. And hopefully, if we check that, we should find that we get 4, 4. Certainly in the first entry, we get minus 12 plus 16, so we get 4. In the second entry, we get minus 4 plus 8, so we get 4. So not all 3 elements of S are needed to span R2. S is a spanning set for R2, but in fact, it has more than you need to be a spanning set for R2. It has some redundancy built into it. You could span R2 with just the subset 2, 1 and 3, 1 of S. So there are a few things going on here. One is to observe that the set 2, 1 and 3, 1 has the same linear span as the set with elements 3, 1, 2, 1, and 1 minus 1. So adding 1 minus 1 into the set of two elements doesn't really add anything new into the span. And we can indeed observe that 1 minus 1 itself, because according to this description, is a linear combination of the other two elements of S. So if you were to drop that element from S, just throw it away, leave yourself with a set of two elements, that set of two elements would have the same linear span as the set of three elements that you started with. If you drop that element from S, you can still recover it in the span of the remaining elements. Okay, so this example gets at the concept of linear independence, which is really our main theme for today. We'll return to it shortly. Just wanted to mention one or two other quick things. One is this distinction between finite dimensional and infinite dimensional vector spaces. So we're going to be this kind of in the next few lectures. So I thought I'll just mention it here. A vector space is finite dimensional if it has a finite spanning set. So if there's a finite set of elements with the property that every element in the vector space is a linear combination of those ones, and a vector space that doesn't have such a finite spanning set is infinite dimensional. Okay, a couple of examples. If we take the vector space of all polynomials with real coefficients, which is denoted by Rx as usual, assertion is that's infinite dimensional. It doesn't have a finite spanning set. And to see that, you just imagine that we take some finite set of polynomials with coefficients in the real numbers. Then each one of those has a highest power of x that appears in it. So maybe it's x to the fourth in one of them and x to the seventh in another one, whatever. Then if you've got a finite set of polynomials, then amongst all of them, there's a highest power of x that appears. And no linear combination of these polynomials can have a higher power of x than that in it. So basically, no matter what finite set of polynomials you take, there's a degree above which its linear combinations can't go. So there's no way that the span of your finite collection of polynomials can be the entire polynomial space Rx. The degrees of the elements that are in the linear span of your finitely many polynomials would be bounded above by the highest degree of any of them. So an example of an infinite dimensional vector space is the full set of polynomials over the real numbers, or over any field indeed. Another example, which is an interesting one, and we might come back to this a bit later just to see why it's actually true, is if we take a set of real numbers, that can be regarded as a vector space over itself, but it can also be regarded as a vector space over the field of rational numbers as the scalars. And if you ask yourself, is there a finite spanning set for the set of real numbers over the field of rational numbers? The answer is no, although it might not be completely obvious. I mean, one way to see it, if you recall some of the things we talked about last year in about cardinality of infinite sets, is that the set of real numbers is a uncountable set. So if you were to take any finite number of elements of the real numbers and take all rational linear combinations of those, that set would actually be countable. It would have, because the rational numbers themselves are countable. So one way to see this is that the set of real numbers is countable. So the span within that of the set of any finite set of vectors with rational coefficients is going to be countable. So it wouldn't be big enough to accommodate all the real numbers. That's kind of a sort of set theory way to see it. We will develop some methods in linear algebra that will allow us to see this in a more, I suppose, in a more algebraic sort of context. One other comment just from the last slide, which I skipped. So just recalling that example in R2. So if we have some subset of a vector space V, so S, and we have some subset of S. Okay, so S1 and S live inside this vector space V. They're just sets. S1 is a subset of S. Then certainly the span of S1 is contained in the span of S, because every linear combination of elements of S1 is a linear combination of elements of S. Potentially, the span of S1 could be equal to the span of S. So basically, this is kind of asking, if we take elements, if we take a set S, throw some elements out of it, can we still recover them in the linear span of what remains? And the answer is that you can do that if and only if each of the elements that you threw out is a linear combination of the ones that are still there, so that you can recover them in the linear span of what remains. Okay, so generally speaking, if you have a set, you can look at its linear span. If you add something else into the set, that's a linear combination of the things that are already in it, then the span of the new set doesn't exceed the span of the original one. Equally well, if you throw something out of a set, but it's a linear combination of the things that are still there, then you haven't really thrown it out of the linear span of what remains. So if one set is contained in another one, then its linear span will be contained in the linear span of the bigger one, but they could be equal. And that just depends on whether ones that you've whether the elements that are in one set but not the other are actually linear combinations of the elements in the smaller set. Okay, that sets us up well for the concept of linear independence. Okay, so just recall that last example of a spanning set of R2 with 3 elements in it, and we realized that, you know, if we threw out one element, we still had a spanning set of R2, and indeed, although we didn't say it at the time, we could have thrown out any one of the 3 of them, and we still would have had a spanning set. We only did that in one case. Okay, so this concept of linear independence is really a hugely important one in linear algebra. I can't overstate its importance. And it's somehow kind of the other side of the coin of the concept of a spanning set, but it's sort of an opposite concept, although not directly. So if we have a subset of a vector space V, and we're going to insist temporarily that our subset has at least 2 elements in it, then we'll say that S is linearly independent if no element of S is a linear combination of the other elements of S. Or equivalently, if no element of S belongs to the span of the other elements of S. Okay, so S is just a subset. Think of it as being a finite subset, although it doesn't have to be. But, you know, think of it as having 3 elements or something like that. It's linearly independent if whenever you throw something out of it, that element cannot be recovered by taking linear combinations of the elements that are remaining. Okay, so it's sort of really gone. When you throw out the element, you're also throwing it out from the span of what's left. So since this definition required this little technical thing of having at least 2 elements in our set, I should also mention that a subset consisting of a single element is also linearly independent, provided that its unique element is not the 0 vector. Okay, so that's what it means to be linearly independent. A set of vectors is linearly independent if no one of its elements is a linear combination of the rest of them. And that, in a way, you could think of it as saying that all of them are needed to span its linear span. If you threw out any of them, you would also lose some of the linear span. Okay, so there are different definitions of linear independence that people think about and that are in the textbooks as well, which have different kind of advantages. So to decide if a given set is linearly independent based on this first version of the definition is kind of not that easy, because if I give you a set of 5 vectors in R3 and I ask you to decide if the set is linearly independent, then if you're taking this definition as your sort of instruction for how to decide that, then you have to look at each one of those 5 elements and check whether it's a linear combination of the other 4. And that is, in principle, maybe like a lot of work, you know, if you have to do it completely independently for all 5 of them. So maybe it's not the most useful if you want to check something. So the alternative definition, which is quite often presented in textbooks as the official definition of linear independence, is actually kind of more convenient for checking that. But personally, I find that this one is kind of easy, kind of sort of captures the real intuitive meaning of the concept more effectively, for me at least, I think for many people. So the second version of the definition. Again, S is a non-empty subset of a vector space. This time we're not insisting that S only have at least 2 elements, it can have only one, but it's not empty. So S is linearly independent if the only way to write the 0 vector in V as a linear combination of the elements of S is by taking all the coefficients of all the elements of S to be 0. Okay, so given any set in a vector space, the 0 vector is always in its linear span, because you can always take the coefficients of all the terms in your linear combination to be 0, and then you get the 0 vector. So if that's the only way to write the 0 vector as a linear combination of the elements in your set, then your set is linearly independent. And this definition, although personally I feel like it doesn't capture the concept quite as well as the first one, actually is more useful in some ways in practical terms, because if you want to check whether some set is linearly independent or not, using the second version of the definition, what you have to do is imagine that you have an expression for 0 as a linear combination of the elements of your set, which probably is just a finite number of them, and try to persuade yourself, or indeed anybody else, that the only way this can happen is if the coefficients in the linear combination are all 0. But it doesn't really encapsulate this concept of like spanning quite the way that the first version of the definition does. So I find it quite useful to be able to kind of move between these 2 versions of the definition to see that they are actually equivalent versions and that they do describe the same concept. Let's just give ourselves a finite set, V1 through Vk, and suppose that according to the first definition that it's not linearly independent. So that V1 in fact is an element of the linear span of the rest of them. So this would be saying in the first definition that the set is not linearly independent. So we have to take a note of that. So this is saying not independent according to the first version of the definition. So S is not independent or not linearly independent according to the first version of the definition. So if V1 is a combination of the rest of them, which means V1 has a description like this, then that's saying that the set S is linearly dependent or not linearly independent according to the first version of the definition. And of course, this statement, this expression for V1 as a linear combination of the rest of the elements of S can be rearranged to give us an expression for the zero element of V as a linear combination of the elements of S. And the coefficients in this expression are not all zero, because at least the coefficient of V1 is not zero, it's -1. So certainly, if a set is not linearly independent according to the first definition, then it's not linearly independent according to the second definition either. On the other hand, suppose that we have a set which is, according to the second definition, not linearly independent. So that means that the zero vector of the vector space V is a linear combination of the elements of the set with some coefficients, C1 to Ck, which are not all zero. Okay, so if the Ci's are not all zero, then at least one of them is not zero, so we can take it after we, let's take it that C1 is not zero. We can relabel the elements if necessary to achieve that. So if C1 is not zero, then the comment is that the equation here can be rearranged to express V1 as a linear combination of V2 through Vk. So we can just write C1 V1 equal to minus C2 V2, etc. And then we're working over a field. So C1 has a multiplicative inverse or reciprocal in our field, and we can just divide that expression through by C1 and say that V1 is this expression, this linear combination of V2 through to Vk. So these coefficients minus Cj over C1, these are all scalars in the field F. But here I just want to mention that we are making essential use here of the fact that our scalars live in a field, which means we can divide by scalars. If you were working over some system of numbers such as the integers, you were just limiting yourself to using integers where you don't have the opportunity to divide necessarily by every scalar, then you would be in a, you wouldn't be able to just do this. So the fact that that our scalars come from fields is actually really, really important here. So the purpose of this slide is just to satisfy us that the two versions of the definition of linear independence are equivalent to each other. You can work with one of them or the other if you want. I find it, as I said, useful to work with both of them in tandem and be able to kind of move between them for sort of conceptual arguments, and also for the purposes of confirming or checking whether some set is linearly independent. Okay. Okay, so here is an example of three vectors in R3. So they're three column vectors written in the usual form of column vectors in R3. And suppose we were asked to verify or to check, to determine whether this is a linearly independent set in R3 or not. So of course, we could set about asking ourselves whether any of these vectors is a linear combination of the other two, and that would work. But the kind of more direct way to do it, I suppose, is to use version 2 of the definition and ask ourselves, can we write the zero vector as a linear combination of these three vectors in S in some other way, other than by choosing the three coefficients of the three of them to be all zero. So if we can, that would be referred to as a non-trivial expression for the zero vector as a linear combination of these three. So that means asking ourselves whether this system of equations, x times the first vector of S plus y times the second one plus z times the third one, all equal to 0, 0, 0, whether that system of equations has solutions other than x, y, z all equal to 0. And of course, if it does, then our study of systems of linear equations tells us, well, okay, so it always has this solution, which is regarded as kind of being the trivial one. If it has other ones, then it must have infinitely many, because you can't have a system of equations that has only 2 or 3 solutions. If it has more than one, then it has infinitely many. And of course, the augmented matrix of this system, so the equations here, the first one says x minus 2y minus 3z equals 0. Second one says 2x plus 3y plus 8z equals 0. The third one says minus x plus 2y plus 3z equals 0. And all three of those would have to be satisfied simultaneously for a solution, for an expression for 0 as a linear combination of these three vectors in S. So here's the augmented matrix. And here, like in these situations, the fourth column is always going to be 0. So you can leave it out if you want, because it remains 0 throughout any row operations that apply. Okay, and indeed, if you do apply elementary row operations to this system, you can already notice that the first and the third row are scalar multiples of each other, So in fact, we are going to get a row full of zeros in the reduced form, because adding the first row to the third one already gives us a row full of zeros. And here is the row reduced echelon form. So again, these three columns correspond to the three variables x, y, z, the fourth column to the right-hand side of the system. And we do observe that z is a free variable here, and that by choosing different values for z, which we can do freely, we're going to get different values for x and y as well. So there are multiple solutions to this attempt to write 0 as a linear combination of the three vectors in S, and our conclusion is going to be that the set S is linearly dependent. So just to write down the solutions, if we let Z be the or if we let T be a parameter that's assigned to the value of Z in a solution of the system, here we see the first equation is saying that X plus Z should be 0. Second equation here is saying that Y plus 2Z should be 0. And as long as you have three numbers, X, Y, and Z, that satisfy both of those two equations, then you have a solution of this system. Okay, so basically x is going to be minus t, y is going to be minus 2t, if z is t. So anything like this is a solution for x, y, and z. And by taking t to be, for example, 1, we'd have x equals minus 1, y equals minus 2, z equals 1, and we can achieve a description of the 0 vector as a linear combination of these three vectors with all three coefficients being not 0. So our conclusion is that S is not linearly independent, and we would say that S is linearly dependent in that case. Okay, so what it means to say that S is linearly dependent is that S is not a minimal spanning set for its linear span. That we could throw something out of S, not necessarily anything, but something, and that we would still have a spanning set for the original span of the three elements of S. In fact, in this particular instance, the fact that we have an expression for the 0 vector as a combination of the three vectors of S where none of the three coefficients is 0 means that we could pull any one of these to the other side of the equation and write any one of these three vectors as a linear combination of the other two. And that means that we could throw out any element from S and leave ourselves with a set of two elements, which would still be a spanning set for the span of the original three. Okay, so here are a few comments about linearly independent sets. And this is a topic, I think, a concept that's really worth spending a bit of time kind of digesting and making friends with, because it turns out it's so important and it's so powerful. And it's really such a key thing in linear algebra. So S is linearly independent if it is a minimal spanning set of its linear span, in the sense that if you throw anything out of S, take any proper subset of S, then the space spanned by that proper subspace is going to be genuinely smaller than the space spanned by the original S. So S is linearly independent if it's a minimal spanning set of its linear span. No proper subset of S spans the same subspace that S does. Or if you like, every proper subset of S spans a strictly smaller subspace than S itself does within the vector space phi. Okay, so that's one way to describe what a linearly independent set is. Another one which can actually be really useful and a very good sort of description to have in your mind is that if S is linearly independent, it means that every element of the linear span of S has a unique expression as a linear combination of elements of S, so a unique description, a unique set of coefficients for each of the vectors in S that describes each element of its span as a linear combination. And so that's quite a useful sort of characterization of what linear independence means, or at least of one property of it. And to see why that's true, like if you had an element that had two different descriptions as a linear combination of elements of S, then subtracting one of those from the other would give you a non-trivial description of the 0 vector as a linear combination of elements of S, where not all the coefficients would be 0. So if a set is linearly independent, that means that there's only one way to write every element in its linear span as a linear combination of those elements. There are no alternative coefficients that would do the same job. So like we saw with that example in R2 earlier, where we had 3 elements and multiple ways to write any vector as a linear combination of them, that was already showing us really that the set was not linearly independent. Okay, and another version of that description, which is sometimes also good to have in our vocabulary, is that the set S is linearly independent. So let's say that S is V1 through Vk or whatever. So what it means to say that every element of the linear span of S has a unique description as a linear combination of the elements of S is that if we take an element V, then there's a unique choice of coefficients A1 down to AK in the field, for which V is equal to A1 V1, and so on down to AK V1. So if the choice of the AI is unique, it's determined by V, then the AI can actually be regarded as sort of like coordinates of the vector V with respect to this spanning set consisting of the elements V1 through Vk. So if S is linearly independent, it means that every element of the span of S has kind of unique coordinates in terms of the elements of S. And so this is something that's quite interesting because it's a key element of the powerful connection between abstract vector spaces and matrices and vectors in the form of like lists of elements. Because what we're saying here is that no matter what our vector space is, like it could be some really abstract thing, some space of polynomials or functions or whatever, something fairly, that it doesn't have a sort of geometric description, let's say. But we're still saying that even in a case like that, the vector space is defined over some field, which is like some system of numbers that has multiplication and division and addition and subtraction. Then we're saying that if we have a spanning set in mind, if we have a linearly independent set in mind, then every element of the span of that linearly independent set has unique coordinates in terms of how it's written as a description, as a linear combination of the elements of that set. And the coordinates are just elements of the field. So basically, the element V here can be fully described once we have the spanning set in mind, if it's linearly independent, by the list of coefficients A1 through AK. So it just looks like a vector in the in the set of column vectors over R or whatever. It just becomes like a list of K numbers. So somehow every vector space, no matter how abstract it is, if it's spanned by some finite linearly independent set, its elements can all be interpreted as just being ordinary sort of column vectors with entries from the field. And those entries are the coordinates of that vector with respect to the particular spanning set. Okay, so a linearly independent set in a vector space V is a minimal or irredundant spanning set for its linear span. Now, if its linear span is the entire vector space V, then what we're talking about is a spanning set for the entire space, which is linearly independent. So with respect to which every vector can be written, every element of the space can be written as a unique linear combination. So a spanning set for the whole space that's also linearly independent gets a special name. It's called a basis. So a basis of a vector space V is a spanning set of V that is linearly independent as well. So it has the property that every element of the entire space has a unique expression as a linear combination of these elements of the basis. And that's like a unique set of coefficients, which can just be regarded as sort of making up a vector with n entries, which come from the field under consideration. Let me just mention that the plural of the word basis is bases. It's the same as the plural of the word base, but it's not the same word. It's the word base. So if I'm talking about bases or different bases of a vector space, that's just the plural of the word basis. So a basis of a vector space V is a spanning set of V that is linearly independent. We will mostly be interested in finite dimensional vector spaces, in which case a basis would be actually a finite set as well, and we can do quite a lot with that. And the fact that everything in our vector spaces can be kind of written in terms of a finite number of elements really gives the whole subject kind of a flavor of sort of discrete maths or combinatorics, even though we are dealing with infinite sets and we're dealing with sets where generally we do have kind of notions like continuity and so on, but we're still able to describe everything in terms of a finite number of sort of basis elements, and that gives us some of the sort of access to some of the kind of methods and approaches that arise in sort of discrete mathematics as well. Okay, so that's it for today. Essentially, we're going to develop this idea a bit more and talk next time we meet, which will be in the first lecture of week 6, about the concept of dimension, which is closely related to that of a basis. Okay, so thank you very much, everybody, and see you next time.